So we have now introduced capacitors in a circuit and resistors in a circuit. And if we have multiple, we know how to combine capacitors into equivalent capacitance. We know how to combine resistors into equivalent resistance. Now we want to talk about what if we put the two in the same circuit. Okay, so to do that, let me introduce a circuit. It's not just a simple circuit. It's got a battery, but there's a switch in it where the capacitor can be connected to the battery or to the resistor. So that switch can go from the battery to the resistor, and we can connect the bottoms this way. So in this configuration, that's capacitor. This will be C, this will be R. Okay. In this configuration, the resistor is not doing anything. No current's flowing through here because that's broken right there. There's no path to complete that circuit. So this would be delta V battery. Okay. And right now, these are connected together, and so the battery has charged the capacitor. And if you wait long enough, and it doesn't take too much time, then this gets fully charged to the point what capacitor will allow. Remember, C is Q over delta V by definition. Okay, so given enough time, this charge will build up on here until this is met. Okay, and once it's met, it's done. It's fully charged. So the question is, well, what if I suddenly then switch that and flip this switch over to here? So now it's connected to there. Now the battery is not in the circuit. The battery has no ability to cause electrons to flow because it's broken or open here. But now we have this charge on this capacitor given by this equation, and it is able to flow through the resistor to cancel out the charge over here. Okay, so this is technically the electrons would flow and go and be collected by the bare positive nuclei. Okay, but we assume positive flow for traditional current. So now current can flow. But think about this. If this is some amount of charge and it starts to flow, well, the amount of charge that's left over is smaller, which means the potential difference ought to be smaller because we know capacitance is purely an object property. It's purely a property of its geometry and composition. It has nothing to do with what charge is on it, just its area and its gap diameter. Okay, so this can't change. So if this gets smaller, this must get smaller. But if this gets smaller, then the effective potential across the resistor gets smaller, which means the current must be getting smaller. And that's going to keep going. And so if we think about it carefully, we don't have a lot of, our intuition right now to build this up. But if we think about the charge on the capacitor as a function of time, it's getting smaller with time. Maybe it's linear like that. Okay. We're going to find that it's actually a decaying exponential. It's actually this curve here. It gets smaller, but the rate at which it gets smaller, meaning initially it loses lots of charge, and then later on it loses very little bits of charge for a long time. Okay, now effectively it'll get so small that it really doesn't matter if it's zero or not. It's a small value and it's so close to zero. But the idea is that it's decreasing. So we're going to try and derive this curve. How do we know it's an exponential, not just like a linear decreasing line? How does that work? And this is a pretty nice derivation. I like this one because it really makes equations, calculus, make physical sense. Okay, so let's do our loop rule. We're going to go around this loop. Okay, we're going to start here, go across this one down here. Now we know current's going to flow this way. So we're going to go in the direction of current across the resistor, which means we get a drop there. Okay, so going from this spot, we first cross the capacitor, which gives us a delta V capacitor, and it's positive. Okay, and then we go in the direction of the current across the resistor, so we get a negative IR, and we get back to where we started, so that's 0. So we use that loop rule, knowing that the potential difference across the full loop, getting back to where we start, must be 0. We gain, we lose. Okay, well, we can rewrite this equation to change the delta VC to V Q over C. Just multiply the delta V up and divide the C down. Minus IR equals 0. We're like, okay, well, what do we do next? The thing to note is that the amount of charge that's on this plate is related to, it's dependent on how much current is flowing across the resistor. Because if the current's big, then this charge is changing fast. Okay, we're losing a lot. And in fact, if you think of the definition of I is defined as dq dt, how much charge is flowing per unit time. So this is the charge that's flowing in the wire, but that charge is opposite the change in charge in here. So if you lose a little dq here, so this gets smaller by a small amount, then that means that q is flowing through here. So we could say this is equal to negative d big Q dt. Again, this is the charge flowing. This is the charge on the plate. If this is big, this is getting small. A big change here is a big negative change here. This is getting smaller and smaller. So we have a minus sign. So we can add that to here, and we get Q over C. Minus a minus gives us a plus. So minus here, algebra minus, definition minus, gives us a plus. dq over dt times r equals 0. Okay. Now that is an equation for charge, and it's sufficient to solve it. Now we can use some calculus to solve it, but to first of all recognize C is a constant. It's wrapped up in this capacitor package. R is a constant. It's wrapped up in this resistor package, and so I can make this look a lot easier when I recognize those are constants. And so I'm going to go ahead and divide the whole thing by R, and I get Q over RC plus dq dt equals 0. Okay. Now I'm going to subtract this to the other side. I get dq over dt equals a negative q over rc. Okay, now if you've taken enough calculus, you may recognize that this is a separable differential equation. So I could collect all the q together on one side and get this time dependence to the other side. And that makes it look like dq over q. So I divide this q down and I multiply this delta t up. I get negative delta t, or dt, sorry, over rc. Now since this side depends only on charge and this side depends only on time, that's called a separable equation, and we can integrate this side from some q naught to some q at some time, which would be related to some t naught to some t at some time. And we could find the charge on the plates at some later time to do this. Okay. All right, so bringing that back up here, this 1 over q, the derivative of what would give you 1 over q? That's the natural log. The derivative of a natural log gives you an inverse, 1 over inverse. So taking that derivative, we get the natural log of q evaluated from q0 to q, right? And is going to equal negative. These are just constants, so I get negative 1 over rc, and I get just, the only thing left is dt, which means I just have t minus t0. Okay. All right, evaluating this at its endpoints, I get natural log of q minus the natural log of q0 equals negative, and I'm going to, this rc, I'm going to say that I'm going to call that a different variable, and I'm going to let t0 equal 0. So I just end up with t over, and I'm going to call this rc tau. It's called the time constant. We use tau as a characteristic time. In this context, it's the time constant. It's the rate at which this charge is decreasing. Okay, the rate at which it decreases here. Okay, now we can use a property of logs over here. That's nice. Log of a minus log of b is the same thing as log of a over the log of b. So this is log of q over q0. Okay. And finally, again, we're trying to find q. We want to see how does q change in time. So if we exponentiate both sides, like that. Well, e to the natural log of something just kills the natural log, and we have q over q0 equals e to the negative t over tau. And then lastly, q equals q0 e to the negative t over tau. Okay. And so we have found a relationship that is a decaying exponential. So it is this shape. And so this is really cool. Capacitors can be used to drive current, but we see that they're not stable. Not like a battery. A battery keeps a potential constant. But with Q changing, its total charge changes in an exponential manner, which makes it difficult to drive current in a stable way. They have their benefits in other regards, in their rechargeability, but they're more difficult to use. And so there's a big debate whether or not capacitors are the future of electrical storage versus batteries. Okay, now we could have done something very similar here and come up with the current would be equal to whatever initial current there was times e to the negative t over tau. We just need to remember that that initial current would be equal to the current when these were full, and when these were full, the voltage was the same as the voltage of the battery. So the I naught in this case would have been the delta V battery divided by R. Okay, so that is an RC circuit. Now I chose to demonstrate the case of a discharging capacitor. This capacitor is discharging its charge through the current through the resistor. We could have done it something differently, where we could have put a resistor maybe right here, okay, and then flip the switch to here, and this will start charging the capacitor, but through a resistor. So that resistance has that resistor slows this. And what we'd find is we'd get an exponential again, but it's charging, and it grows to Q final, some established Q final, which would be given by this relationship. But I'll leave that for the text, but just know that the same idea would be held to find a charging capacitor across the resistor, where we discharged a capacitor across the resistor in this example.